the goal of the Kalman filter is going to be to learn the time-evolving conditional posterior distribution of the state sequence, the hidden state sequence, given the observed data up until that time for a given sequence x1 through xt. And again, to review, we have this sort of a model where we say that the underlying state at time t plus 1, given the underlying state at time t, is a multivariate Gaussian, like this. And the distribution on the observed value at time t, given the underlying state at time t, is a multivariate Gaussian, parameterized like this. So let's look at how we can calculate this conditional posterior distribution. Well, we use Bayes' rule, as usual, in order to figure this thing out. We can say that the conditional posterior of my hidden state at time t, given all of the data up until and including time t, is proportional to the likelihood of what I observe at time t, given the state at time t, times the conditional posterior distribution of the state at time t, given all of the data up until time t minus 1, but not including time t. So this is the first step in solving this problem. We then represent this prior distribution as a marginal distribution. So we say that the distribution on the state at time t, given the data up until time t minus 1, is equal to an integral. So to be more explicit, we have this integral of st and st minus 1, given the data from 1 to t minus 1, dst minus 1. So we simply add the state at time t minus 1 and then integrate it out to get a marginal. But then we write this joint distribution as a conditional distribution on the state at time t, given the state at time t minus 1, times the posterior distribution on the state at time t minus 1, given the sequence up until time t minus 1. So originally we had x1 through t minus 1 in here, but if you tell me the state at time t minus 1, then the state at time t is conditionally independent of the sequence x up until time t minus 1. So we could get rid of the sequence in this conditioning here. So we write this prior distribution as this marginal, and notice that this marginal includes the transition distribution and the posterior distribution for the previous time point. So this is part of the story of Bayes' online learning with Bayes' rule, where the posterior at the previous time point is used to form the prior at the next time point. All right, so we've decomposed this problem into parts that we do and don't know. So we've said that the posterior distribution on the state at time t, given the sequence of observations up until and including time t, is proportional to the likelihood of the observation at time t, given the state at time t. By definition of the model, that's a Gaussian with this mean and this variance. So notice that the Gaussian has the state in the mean there, times the prior, which we've written as a marginal, of the transition distribution from state at time t minus 1 to time t, which we've defined by the model to be a Gaussian with this distribution, times the posterior of the previous state at the last time point, given the observations up until the last time point. So we don't know what this one is yet. So let's make some observations before we continue working through this problem. Again, first we want to note that the left-hand side has the posterior, the conditional posterior on st, and the right has the conditional posterior on st minus 1. So we already kind of have a hint that if we can solve the posterior at the previous time, we might be able to solve the posterior at the current time. We know that we want this integral to be in closed form in order to make things work out well. So this is a motivation in how we want to pick distributions. And we also want this likelihood and this prior, so the integral constitutes the prior, we want that pair to also lead to a posterior that is known. So we would like these two to be conjugate to each other if possible, meaning that the posterior has a nice closed form solution and is in the same family as the prior. And we want whatever this turns out to be to then also make future calculations easy. So we want this to work out well. And so it all hinges on what this distribution is. We've already picked Gaussians here, and so we need this to be something nice. So for now, let's just hypothesize temporarily that this unknown Gaussian, this unknown posterior distribution at time t-1 is a Gaussian. Let's say that this conditional posterior at the last time point is a Gaussian with mean vector mu and covariance sigma by hypothesis. And if this were true, what would the solution to this posterior be? Okay, so proceeding from this hypothesis now, we have all the distributions in here, and we can start calculating things. First, we have to calculate this marginal. So a nice property of Gaussians is that the marginals are still Gaussian, meaning that if we have a distribution like this, where we have ST as a Gaussian with this mean and this covariance, and then a prior distribution on ST like this, which is a Gaussian with mean mu and covariance sigma, we multiply those two together, and then we integrate out the state at time t-1. So we're integrating out st-1 here and here in this multiplication. The result is still a Gaussian, so we still have a distribution on ST, which is a Gaussian with mean equal to C mu. So notice that we've taken st-1 here and replaced it with the mean of the prior. So we've got C now times mu as the mean. And the covariance equal to Q, that's from this likelihood, plus C times sigma times C transpose. So there's the sigma there, and there's the C there. We assume we know all of these. We're assuming we know this, this distribution by hypothesis, and we know C and Q by the model definition. So this marginal likelihood here to calculate the prior on ST is a Gaussian with a mean and a covariance, all of which we can calculate. So now we've solved for the integral. We still want to calculate this conditional posterior at time t. So now it all hinges on whether this likelihood times this prior is something that we can now normalize and calculate the posterior. So again, the likelihood of xt is a Gaussian with mean d times the state at st times the covariance. And the prior on the state at time t is equal to a multivariate Gaussian with this mean and this covariance calculated on the previous slide. And so again, we're working with Gaussians, and a nice property is that the posterior is again a Gaussian. So the posterior distribution on ST is a Gaussian. So when we normalize this thing so that it is a function of ST that integrates to 1, we find that we have a Gaussian with mean mu prime and covariance sigma prime, where the covariance is equal to this and the mean is equal to this. So it looks complicated, but notice that it's a function of everything that we know. So here we have the prior covariance. Here we have a function of d and v, which is simply from the likelihood. In this term, we have, again, a function of d and v and the observed data and a prior term. So all of these things are something we can calculate. So we plug in the relevant values, and we get this conditional posterior. Okay, so we've solved for the conditional posterior, but we made a hypothesis. Remember that we said that we're going to hypothesize that this conditional posterior at time t-1, given all of the data up until time t-1, is a multivariate Gaussian with a mean and a covariance. So we hypothesized that, and based on that hypothesis, we were able to show that therefore the conditional posterior at the next time point would also be a multivariate Gaussian with a mean and a covariance equal to a function of things that we know. Therefore, in order to turn that hypothesis into the truth, all we need to do is define a Gaussian prior on the first state. So for the prior definition on the state at time 0, the starting state, Remember, if t is equal to 1, then here we have a prior distribution on the state at time 0. We don't have any data yet, so that's just the starting state, the prior on the starting state. We get to make that, we get to define that prior distribution. And so if we define that to be a Gaussian, for example, a Gaussian with 0 mean and identity covariance, or any other multivariate Gaussian that we want that would make sense for our problem, then by definition, this first prior at time equal to 0 is a multivariate Gaussian, and therefore everything follows through in order, where the conditional posterior at time 1 is a multivariate Gaussian because we've defined the prior at time 0 to be a multivariate Gaussian. And that can get the ball rolling. That will make everything Gaussian downstream. So we've shown with the Kalman filter that when we want to calculate the sequence of conditional posteriors on the state, the latent state, since we're working with Gaussians, since we made modeling assumptions where everything's Gaussian, it all is in closed form and can be done using simple functions of things that we know. There's one other quantity that we might want to calculate with this Kalman filter, and that's predicting the observation at the next time point. So we've shown how to calculate the conditional posterior on the state at time t, given the observations up until time t. But what if we want to then take that and predict the observation at time t plus 1 before we get to see it? And so what we're asking is, what is the distribution on the observation at time t plus 1, given all of the observations up to and including time t? This is the distribution that we're interested in. It's our predictive distribution on the next observation. Well, we write this as a marginal over the state, where again, what I'm doing here is writing p of x at time t plus 1, comma st plus 1, given the data up until time t, integrating out s at time t plus 1. So I have this joint distribution of the observation at the time t plus 1 and the state at time t plus 1. I integrate out the state at time t plus 1 to get this marginal distribution. But now I write this conditional this joint distribution as a conditional distribution on the observation at time t plus 1, given the state at time t plus 1, times the conditional distribution of the state at time t plus 1, given the data up until and including time t, but not t plus 1. So here, I'm not conditioning on any of the other data, because if you tell me what the state is at time t plus 1, my observation at time t plus 1 is independent of all of the other data. All right, and now we again do the same breakdown of this distribution, where I write this thing as a marginal of the state at time t plus 1 and the state at time t, given the data up until and including time t. But now I marginalize out the state at time t. But I take this joint distribution and I factorize this as well into the conditional of the state at time t plus 1, given the state at time t, times the conditional of the state at time t, given all of the data up until and including time t, which is just the posterior distribution which I have. We've discussed how to calculate this. So this is how we can take the marginal predictive distribution and write it as an integral over distributions we know. Again, the distribution of the data at time t plus 1, given the state at time t plus 1, is just a Gaussian with this parameterization by the definition of the model. The transition distribution on the state at time t plus 1, given the state at time t, is just this Gaussian, again by definition of the model. And the conditional posterior of the state at time t, given all the data up until and including time t, has been calculated using the Kalman filtering algorithm from the previous slides. So we plug in a Gaussian here with mean mu prime and sigma, a covariance sigma prime, plug in a Gaussian here with parameters defined by the model, and a Gaussian here. And notice that we're integrating out st and st plus 1. So we end up with just a function of the data at time t plus 1 and the data up until time t. Again, these are all Gaussians. We've already discussed how we can take this marginal and get a Gaussian out of it. And then if we have a Gaussian here, we can again take the same marginal and get another Gaussian. I'm omitting the mean and the covariance of this Gaussian, but it's still a Gaussian. It's going to be much more complicated than what we've discussed previously. So we showed this marginal distribution. This was one marginal that we took of a Gaussian with another Gaussian. It became this Gaussian. We would simply have an even more complex Gaussian. For example, here, the mean and the covariance will have this function. And so then we take that, integrate that out, integrate again. So we'll get a very complicated function, but we ultimately get a Gaussian with a mean vector that's a function of things that we know, and a covariance matrix that's also a function of things that we know.